Temperature is supposed to drop the farther you move from the sun. Two Voyager probes, built in 1977 only to photograph planets, kept flying decades past their expiration date into space. No instrument on board was ever designed to measure. They were never built to detect what came next. Something out there did not match a single equation NASA had prepared for. Why these two probes even made it this far? Voyager 1 and Voyager 2 launched separately in 1977, just weeks apart, built for a 5-year mission to fly past Jupiter and Saturn. Voyager 2 got extra assignments, flying onto Uranus and Neptune, becoming the only spacecraft to ever visit either planet. Once the flybys ended, both spacecraft kept flying outward on completely different paths, aimed at different parts of the sky, which is why they would later cross the edge of the solar system at different times and different distances from the sun. Nobody who built these machines in the 1970s expected them to still be sending back data decades later, let alone from a region no human instrument had ever reached. The plan was always simple: point them at the outer planets and see what happens afterward. What happened afterward turned two aging planetary probes into the only two objects that have ever measured what happens, where the sun's influence runs out. The crossing NASA took a year to confirm. On August 25, 2012, Voyager 1 crossed into interstellar space, the region beyond the sun's protective bubble called the heliosphere. NASA did not confirm this until September 12, 2013, over a year later, because Voyager 1's plasma instrument, the device meant to directly measure the density of charged particles around it, had stopped working years earlier. Scientists needed another way to prove the crossing really happened, and they got lucky. In March 2012, a burst of solar material called a coronal mass ejection reached Voyager 1, causing nearby plasma to vibrate in a way the spacecraft's plasma wave instrument could still detect. Those vibrations let scientists calculate the plasma density directly, and the number came back about 40 times higher than anything measured inside the solar wind, exactly what a true interstellar crossing should look like. Voyager 2 followed on November 5, 2018, this time with a working plasma instrument that confirmed the moment immediately. Confirming the crossing should have settled every question about what Voyager 1 had actually flown into. Instead, both spacecraft had already stumbled onto a separate mystery years earlier, one that forced scientists to throw out a decades-old picture of what the edge of the solar system even looked like. The foam nobody expected to find. For decades, scientists pictured the outer edge of the heliosphere as smooth, with the sun's magnetic field curving gently outward and folding back like arcs on a globe. Voyager 1 started picking up something different around 2007, and Voyager 2 picked up the same pattern about a year later. Instead of smooth curving lines, both spacecraft flew through a chaotic patchwork of magnetic bubbles, some roughly 1 astronomical unit wide, packed together like a sea of foam. University of Maryland physicist Jim Drake, who worked on the discovery, admitted nobody on the team had expected to find anything like it out there. The bubbles form through a process called magnetic reconnection, where the sun's magnetic field flips direction near its equator in a rippling pattern. And as the solar wind slows down near the edge of the heliosphere, those flipping sections get squeezed together until they snap apart into self-contained loops. NASA announced the discovery in June 2011, forcing a real rewrite of the textbook model, since a foamy, porous boundary behaves very differently from a smooth one when it comes to blocking radiation from the rest of the galaxy. Around the same time, at roughly 113 astronomical units from the Sun, Voyager 1 detected a separate stagnation region, a stretch of space where the outward speed of the solar wind dropped to 0, the magnetic field intensity doubled, and high-energy electrons from the galaxy shot up by a factor of 100. None of those three changes were predicted together in any model that existed before Voyager reached that distance. A foam made of bubbles was already stranger than anyone had planned for, and it set the stage for an even bigger surprise once Voyager 1 finally reached the true edge a year later. What was actually hiding in the data scientists expected one clear sign above all others when Voyager 1 left the solar system: a change in the direction of the magnetic field around it. Inside the heliosphere, the sun's own magnetic field wraps around the spacecraft in a predictable spiral shape. Beyond the heliopause, a different magnetic field created by the wider galaxy should take over, pointing in a new direction. When Voyager 1 crossed, the field strength did jump, roughly doubling almost overnight. But the direction barely moved at all, staying locked within a couple degrees of the same spiral pattern from inside the solar system. Scientists had built their entire prediction around a field that would visibly rotate, and it simply did not. Some researchers, including 2 senior members of the Voyager team, argued for years that this meant Voyager 1 had not truly left the solar system at all, and had instead entered a strange transitional layer nicknamed the Magnetic Highway. That disagreement was not settled quietly. It split scientists into opposing camps, and one side accused the other of misreading the most important handoff in the mission's history. Why this did not settle the argument? The plasma density evidence eventually won out, and most of the scientific community accepted that Voyager 1 crossed the heliopause on the date NASA announced. But the magnetic field mystery was never fully solved, only explained around. Researchers proposed that the interstellar magnetic field gets dragged and twisted as it drapes across the outside of the heliosphere, bending it into nearly the same direction as the sun's own field, which would explain why Voyager 1 saw so little change. Other physicists blame temporary disturbances from solar storms passing through at exactly the wrong moment. A small number of scientists, including 2 of the mission's own team members, held out and never fully accepted the official crossing date, publishing their own competing models years afterward. NASA's own statement conceded that most researchers had simply abandoned the assumption that a direction change was even required, adjusting the theory instead of the evidence. A magnetic field refusing to behave was strange enough on its own, but at almost the same time, a completely different NASA spacecraft was staring at the same boundary and finding something even harder to explain. The other probe's ribbon nobody predicted. In 2008, NASA launched a small spacecraft called IBEX, the Interstellar Boundary Explorer, built to map the edge of the solar system from orbit around Earth without ever traveling there itself. IBEX worked by catching particles called energetic neutral atoms, fast-moving atoms with no electric charge, created when the solar wind collides with gas drifting in from outside the solar system. In October 2009, IBEX finished its first full map of the sky, and the result stunned the team that built it. Instead of a smooth, even glow of particles across the boundary, the map showed a bright, narrow, curving band of intense activity that nobody had predicted and no existing model could explain. Scientists nicknamed it simply the ribbon. 6 separate explanations were proposed within the first few years, and none of them fully matched everything the data showed. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. A ribbon nobody predicted meant NASA needed an entirely new theory, just to explain why one stretch of the boundary behaved differently from every other stretch around it. The theory NASA is still testing. In 2013, a team led by physicist Nathan Schwadron at the University of New Hampshire proposed what became known as the retention theory. The idea is that some particles from the solar wind travel outward, lose an electron near the true edge of the heliosphere, get pulled along interstellar magnetic field lines for a few years, and then get sent back toward the sun as neutral atoms, lighting up exactly where IBEX detects the ribbon. This explained the ribbon's narrow width for the first time, something earlier theories had failed to do. It did not end the debate. Later research, led by scientist Eric Zernstein at the Southwest Research Institute, described a related process where returning particles bounce back toward the sun over roughly 3 to 6 years, matching IBEX's own observations. Both theories still compete for acceptance today, and NASA has never claimed either one is fully proven. Testing which theory was correct meant NASA needed a much sharper set of eyes on the boundary than IBEX alone could provide. And that upgrade would take over a decade to arrive. The wall of fire that shouldn't exist. In June 2025, researchers combining years of Voyager data confirmed something that sounded almost impossible. Right at the heliopause, plasma temperatures spike to between 30,000 and 50,000 Kelvin, roughly 54,000 to 90,000 degrees Fahrenheit. Reporters quickly nicknamed it the Wall of Fire. Heat that extreme should destroy almost anything, yet both Voyager spacecraft passed straight through unharmed. The explanation comes down to density, not intensity. The particles at that boundary carry enormous energy individually, which is what temperature actually measures. But there are so few of them spread across such a vast area that almost no heat can transfer to a solid object passing through. A spacecraft could sit inside that zone indefinitely and never feel warm, because feeling heat requires trillions of particles colliding with something every second, and out there, the particles are spread thin enough that meaningful collisions almost never happen. Surviving a 50,000 degree wall without a scratch is the kind of detail that sounds made up, and it is exactly the sort of finding that only decades of aging hardware could have delivered. Hardware that is now running out of the power it needs to keep watching. The probes running out of power. Both Voyagers run on radioisotope thermoelectric generators, devices that turn heat from decaying plutonium into electricity, and both lose about 4 watts of power every year with no way to refuel. To stretch the mission, NASA has been shutting down instruments one at a time in an order planned years in advance. Voyager 2 lost its plasma science instrument in September 2024. Then Voyager 1 lost its cosmic ray subsystem in February 2025. Then Voyager 2 lost its low-energy charged particle instrument in March 2025. Voyager 1 lost that same instrument on April 17, 2026, dropping it down to just 2 working instruments, a magnetometer and a plasma wave detector. Voyager 1 now sits more than 15 billion miles from Earth, so far that a single command takes about 23 hours just to arrive. Engineers are testing a power-saving procedure nicknamed the Big Bang on Voyager 2 in 2026, hoping it can keep at least one instrument running into the 2030s on each spacecraft. Every instrument NASA switches off is a permanent loss of one more way to study a region nothing else has ever reached, which is exactly why a brand new mission was already on its way before the last shutdown even happened. The new mission sent to finish the job. On September 24th, 2025, NASA launched IMAP, the Interstellar Mapping and Acceleration Probe built to pick up where IBEX and the Voyagers left off. IMAP reached its permanent post at a stable point in space called L1, about 1 million miles from Earth toward the Sun in January 2026, and began its primary science mission on February 1st, 2026. Its instruments collect energetic neutral atoms with far greater sensitivity than IBEX ever could, revisiting the ribbon every few months instead of once a year, and mapping the boundary in sharper detail than any previous mission. Led by physicist David McComas, the same scientist who ran IBEX for over a decade, IMAP is meant to finally settle which theory about the ribbon holds up, and to keep watching the wall of fire discovered by the aging Voyagers, this time with instruments built for exactly that job. IMAP now sits watching the same boundary that confused scientists for over a decade, while the two spacecraft that started this entire mystery keep drifting further into the dark with less power every year. What comes next? Voyager 1 and Voyager 2 are still out there right now, still transmitting, still the only human-made objects that have ever directly touched interstellar space. Nothing about the wall of fire, the magnetic foam, the field that would not turn, or the ribbon nobody predicted has been fully solved. What NASA does know is that the edge of the solar system is not a quiet fade into empty space. It is an active, unpredictable boundary that keeps producing results nobody's models expected, using instruments built in the 1970s that were never designed to look for any of it. IMAP will spend the next several years trying to finish the story. Two dying probes started by accident, simply by refusing to stop working. If this kind of deep space mystery is something you want more of, subscribing helps this channel keep digging into what NASA finds next. If you enjoyed this video, make sure to subscribe, and I'll see you in the next video.